Hi, my name is Excellent Joy Ferrer, and I will be discussing about the petrology and tectonics of Phanerozoic continent formation from island arcs to accretion and continental arc magmatism. So in this presentation, I have 7 parts to tackle, starting with the introduction, objectives, RRL, methodology, data, discussion, and conclusion. First off, the introduction. The continental crust represents only 0.6% of the Earth's mantle, but it accounts for 30 to 50% of the Earth's budget of highly incompatible trace elements. So these elements are depleted in the Earth's upper mantle, suggesting that the cumulative formation of continental crust is efficiently extracted by these elements from the mantle into the crust itself. So there's this thing called global crustal paradox. A global paradox which explains that there is a major element perspective. And from this perspective, according to this article, mantle melts are basaltic and hence mafic. So it is low in silica and high in magnesium. Yet, the continental crust on average is thought to be andesitic and hence felsic. So it is higher in silica and lower in magnesium. This global paradox is further exemplified by the fact that although a significant fraction of Phanerozoic continental crust appears to be formed by island arc accretion that is integrated by vertical sections of island arcs, before they have accreted to form continents, they are still basaltic. These island arc basalts must therefore have differentiated into felsic and mafic complements, the latter being hidden beneath the seismic moho to drive the remaining crust to felsic compositions. So, according to this article, this is only what is known, but something that is not fully understood is exactly how and when island arcs differentiate, how arcs assemble into continents, and how all of these processes are intertwined. That is why this paper focuses on the global crustal paradox from the perspective of Phanerozoic continent formation. So next is the PRB and the SNB. So this study also focuses on the Peninsula Ranges batholith or the PRB and the Sierra Nevada batholith or the SNB, which are the eroded remnants of Mesozoic continental arcs formed on the edge of the Precambrian North American craton by subduction of the Farallon oceanic plate beneath North America. These two were emplaced between 125 to 85 million years ago and 120 to 89 million years ago, respectively, and within these time intervals, Plutonism migrated from west to east away from the trench. So the objectives of this article is to link the petrogenetic and tectonic processes involved in making continental crust, give a three-dimensional view of crust which permits the petrogenesis and tectonics of Phanerozoic crust formation to be linked in space and time, and then to establish a baseline which crust types which young and old can be compared. So based on the previous works that aids with this study, we have investigated 287 plutonic samples collected by Baird in 1979 on a uniform grid in the Cretaceous Northern Peninsular Ranges batholiths or the PRB in Southern California. So, one of Baird's goals was to extract representative compositions of each pluton. As I have said a while ago, the PRB and the SNB were in place between 125 to 85 million years ago and 120 to 89 million years ago, respectively, and within these time intervals, Plutonism migrated from west to east away from the trench. For methodology, there are 287 plutonic samples collected by Baird in 1979, and he collected samples from each of the four corners of the 400 by 400 foot square centered on a given grid point, and then two samples from each corner were collected, making a total of 8 samples per locality. And lastly, there is a geochemical sampling of a batholith. So the figure 2 here shows the location of the eroded remnants of Mesozoic continental arcs formed on the edge of the Precambrian North American craton by subduction of the Farallon oceanic plate beneath North America, which are the Peninsular Ranges batholith and the Sierra Nevada batholith. The dotted line here represents the inferior edge of Paleozoic North America. The blue dashed line in the Peninsular Ranges batholith, or the PRB, represents the suture between Triassic-Jurassic island terrains and Paleozoic North America. For the figure B, red triangles represent active volcanoes in the Cascades Arc. Star represents Sinolith, locality for Sierra Garnet pyroxenite. Sample locations from the grid-based study in the PRB includes the red circles that represent samples of plutons east of the tectonic suture, or the eastern PRB. The white circle represents the western plutons, or the western PRB, and the blue line represents the tectonic suture. So figure C is the conceptual model of lateral growth of the North American continent by island arc accretion and subsequent continental arc magmatism in the Mesozoic. So the C1 is the fringing arc, is formed just off the edge of the North American in an extensional environment due to the trench associated with subduction of old oceanic lithosphere that is probably Triassic or Jurassic. The C2 is as the age of the subducting slab sinks, trench retreat subsides, and the black arc closes, resulting in the accretion of the fringing arc to the Paleozoic continental margin, and the formation of the tectonic suture is probably Jurassic. So the C3, further younging of the subducting slab results in trench advance, generating arc magmatism through the newly accreted terrain. The younging of the subducting slab eventually manifests itself in the form of shallowing subduction zone, causing arc magmatism to migrate eastwards through the suture zone and into Paleozoic North America. Next is the C4. It leaves behind a continental crust biased towards felsic composition. So for D, basaltic magmas stall at depths as they ascend through the lithosphere. So magmas ascending through thick North American lithosphere are forced to crystallize dense garnet pyroxenite cumulates at depth. Magmas ascending through the thinner accreted lithosphere do not crystallize dense garnet bearing cumulates. So next is this figure is the new geochemical data on plutonic rocks from the Peninsular Ranges batholith, or the PRB. Western PRB plutons are denoted by white circles, and Eastern PRB plutons are denoted by red circles. So the dashed white envelope represents Field of Cascade Volcanics, or the JOROC database, and yellow shaded envelope represents Field of Plutons from the Sierra Nevada batholith, or the SNB. Sierra Garnet pyroxenites are denoted as squares, as we can see in the figure, And then large red squares represent high magnesium oxide or pyroxenite, and small orange squares represent low magnesium oxide pyroxenites. So A is the initials as our isotopic compositions are plotted versus the whole rack of SiO2 content. B is MgO versus SiO2, and C is the atomic number of magnesium and magnesium plus iron versus SiO2. D is Al2O3 versus SiO2. E is GD over YB ratio versus SiO2. Inset shows a histogram of GD over YB ratios of magmas calculated to be in equilibrium with Sharon garnet pyroxenites, whose compositions were reconstructed from mineral compositions that are determined by laser ablation, inductively coupled, and plasma mass, that is inductively coupled plasma mass spectrometry. Average of Eastern PRB denoted along with that of globally average upper. So large open diamonds represents magma compositions calculated to be in equilibrium with Sharon garnet pyroxenites. So F is SR over Y versus Y. So this figure is just a simplified version of figure 2b, wherein modal fractionation curves are shown. The lines composed of black circles represents the liquid line of descent caused by fractional crystallization of olivine from a primary basalt. The red arrow line shows the fractional crystallization of Sharon garnet pyroxenites. The thick black arrowed line shows the fractional crystallization of Sharon garnet pyroxenites plus magmatic recharge of primitive arc basalt, or the total mass of magma to be at a steady state. So a complementary crystalline of descent during recharge crystallization process is shown as dashed arrowed line. So the subduction of the Farallon Plate beneath North America is characterized by trench retreat and a slab rollback because old and cold oceanic lithosphere was being subducted. It is also generated by an extensional subduction zone, which created fringing island arcs. Continued subduction. Continental arc was born, and a progressively more compressional environment is developed. So refinement into a felsic crust occurred after accretion. There is an interaction of these basaltic magmas with pre-existing crust and lithospheric mantle created garnet pyroxenitic mafic accumulates by fractional crystallization at depth. So gabbro-wicking garnet pyroxenitic resides at shallower levels by melting of pre-existing lower crust. Our grid-based sampling allows us to estimate an unbiased average upper crustal composition for the peninsular ranges batholith. So the laminated Sharon garnet pyroxenites have some of the lowest UPB ratios ever measured for silicate rocks. So for the conclusion, continental crust was formed through island arc formation, followed by arc accretion and ending with continental arc magmatism. So the differentiation into felsic crust and mafic garnet pyroxenitic lower crust occurs only after accretion, that is in the continental arc stage. So the delamination of the mafic component thus occurs during and after the continental arc stage, not during the life of the island arc. So, mature continental arcs and globally average continental crust have many compositional similarities, suggesting that caldera crust forming processes may operate commonly over space and time. Small discrepancies in some elements imply that other crust forming processes, such as intraplate magmatism, are still necessary to explain continent formation in their entirety. At the end of the study, even though it is generally believed that arc magmatism plays an important role in the formation of continents, exactly how arcs assemble into continents and evolve into felsic crust is not clear. It is not yet concluded. So we show this article shows that from a North American Cordilleran perspective, that continental crust here was formed, assembled and refined through a multi-step process that starts with island arc formation and then by arc accretion and ending with continental arc magmatism. So the differentiation into felsic crust and mafic garnet pyroxenetic lower crust occurs only after accretion. So that is in the continental arc stage. So the delamination of the mafic component occurs during and after the continental arc stage, not during the life of the island arc. That is all. Thank you.